So this is problem session 2 for Calc 1. The lectures are all on YouTube, and what I want to do in these morning sessions is always answer questions about anything or spend time working problems. Any questions before we start? So what's very important in calculus is to understand straight lines. And there are some problems on straight lines, linear models in section 1.2. And I will do some of the homework problems there. So let's start. So in section 1.2, numbers 23, for example. So we have the line y equal 4x minus 3. So, you know, if you have the standard slope-intercept form for a line, y equals mx plus b, m is the slope and b is the y-intercept. So for this line, the slope is 4 and the y-intercept is minus 3. So if you were to graph this line, here is minus 3. That's the y-intercept. And to say the slope is 4 means you go over 1, you go up 4. Go over another 1, you go up another 4. And this line looks like that. Any questions about this? In problem 24, the line is minus x plus y equals 1. So to find the slope and the y-intercept, the best thing to do is to try to write the equation in this form. So this is the same as y equals x plus 1, or 1 times x plus 1. So the slope is 1, the y-intercept is 1. So the line is simply this, y equals x plus 1. In number 26, the equation of the line is given as 6x minus 5y equals 15. So again, you want to rearrange this. This is 5y equals 6x minus 15 divided by 5, y equals 6 over 5x minus 3. So the slope is 6/5, and the y-intercept is minus 3. So here's the y-intercept, and 6/5, a little bit more than 1. The line goes up something like this. Yeah, looks more like that. Okay. Any questions about this? Any of this? In problem 29, we want to find the equation of the line if it passes through the point 0, 3 and has slope 3/4. Well, 0, 3 is right there. That means this is the y-intercept. So the equation of the line is 3/4 x plus 3. In number 33, we have a line that goes through the point 3 minus 2 and has slope 3. So what does it look like? Here's the point 3 minus 2. The line goes through this point with slope 3. What's the equation of the line? Well, we can do this in a couple of ways. One is we could use the slope-intercept formula, y equals mx plus b. We know that m is the slope is 3, but we don't know b. So y is 3x plus b, and what is b? Well, but we're also told the line passes through the point 3 minus 2. So y is minus 2 when x is 3. So b satisfies this equation. b is equal to minus 2 minus 9 minus 11. So this equation is y equals 3x minus 11. So that's one way to solve the problem. A second way to solve the problem is to use the point slope formula. So the line through the point x1, y1 with slope m is y equals m x minus x1 plus y1. And in this case, x1, y1 is the point 3 minus 2, and m is equal to 3. So y is 3, x minus 3 plus minus 2. That's 3x minus 9 minus 2, or 3x minus 11, which is just what we got before. All right. Questions about any of these? Or any other homework problems that you might like me to do?
Professor, I can't seem to find the homework problems.
Sorry?
I can't find the homework problems. I could only see the due dates.
So, you know, you have the course calendar, the syllabus, is correct?
Oh, those are the, oh, okay, sorry.
And
So
the problems for every lesson are exactly what's written on this.
okay, thank you. Sorry, I was confused.
Yeah. So for example, where it says lesson 2, limits, section 2.2, the homework problems are in section 2.2, numbers 1, 3, 5, 11, and so on. And so all the homework for the semester is on the syllabus.
Thank you very much.
Yep.
Excuse me.
Can you speak up? Your voice is very soft.
You don't hear me?
No, I can't hear you.
I'm gonna just type it.
I'm sorry. Do you have a question?
She said she was going to type it instead.
Can you hear me now?
Yeah, now I can hear you.
Can you go over 49?
In this section?
Yeah, in 1.2.
Good. So section 1.2, number 49. So 49 says to use 46 to solve a certain problem. So problem 46 says the following. Suppose you have a line which has the y-intercept at B. So this point is 0B. And it also has the x-intercept at A. So this is the point A0. And we have the line that intersects the x-axis at A and the y-axis at B. This was just the problem in 46. And we're told that the equation of this line is x over A plus y over B equals 1. Okay. At least in the case when you can't divide by 0, A is not 0 and B is not 0. So the line doesn't go through the origin, but it crosses the x-axis at A and the y-axis at B, and that's the equation. And in number 49, we're asked to use this to find the equation of the line which has x-intercept A, y-intercept A, and passes through the point 1, 2. So if this line goes through the point A0, the x-intercept is A. If it goes through the point 0A, the y-intercept is also A. So the equation of the line, we don't know what A is yet, but it's going to be x over A plus y over a equals 1. But we're told that the point 1, 2 lies on the line. So if you let x equal 1 and y equal 2, it satisfies this equation. In other words, 1 over a plus 2 over a equals 1. But 1 over a and 2 over a, you add it up, you get 3 over a. So 3 over a is 1, so a has to be 3, which means that the line is x over 3 plus y over 3 equals 1. And that's the equation of the line. You can also write that as x plus y equals 3 if you multiply by 3, or y equals 3 minus x. So each of these are the equation of the line, just different forms of it. Okay. But the secret to the problem is just to understand that if the x and y intercepts are a equals b, the equation is x over a plus y over a equals 1. And if you know one point x and y that the line goes through, and we're told it's the point 1, 2, then you can use that to calculate a. If you want to prove this expression, so this is the proof or the solution to problem 46, we're told that the line has x-intercept a and y-intercept b. So what is the slope of this line? As you go from here to here, the slope is the line goes down minus b, and from 0 to a is minus b over a. This line has slope minus b over a. So the slope-intercept form of the line will be y equals mx, m is minus b over a, x, plus b. If you bring this on the other side, you get b over ax plus y equals b. If you divide by b, you get x over a plus y over b equals 1. So this is, if you like, a proof that the line with x-intercept a and y-intercept b has this equation. Right. Other questions on any of the homework? So this is all kind of a pre-calculus review in chapter 1, and calculus proper starts in chapter 2 with this idea of a limit. And let me just say a few words about what limits are all about. So let's just give a couple of examples. Here's one very simple kind of example. Suppose we have a function like f of x equals 1 over x, which is defined for x different from 0. So the graph looks like this. And if you look at this graph, you see that as x goes to infinity, this is y equals 1 over x. 1 over x, it's positive, but it's approaching 0. So we would say that the limit of 1 over x as x goes to infinity is 0, because this curve is asymptotically approaching 0 as x goes to infinity. But there's another kind of limit, which is the example the book starts with. Suppose you take the function f of x equals x cubed minus 1 over x minus 1, but you can't divide by 0, so this is only defined for x different from 1. So for every x different from 1, f of x is some number. And what we can ask, even though we're not allowed to evaluate this at x equal 1, is there some limit as x approaches 1, this is the notation we use, for this function f of x? Does this equal L for some number L? Now, if you're in your calculus lab and you have a computer, you could ask your computer to graph this function. And if you do, you would see it's a graph that looks sort of like this, but right here at x equal 1, I put a hole because it's not defined. Nonetheless, it looks like as x gets closer to 1 from the right or the left, the value of the function is approaching 3. And if you did some calculations, if you made a table, as you will see in the book, and you evaluate this function for numbers getting closer and closer to 1, it looks like this limit is approaching, that the function is approaching the limit 3. And if you learned or remember a little bit about factoring, you can actually prove that. Because the way this function is written, you can't divide by 0, so x can't be equal to 1. On the other hand, you can factor. So for x different from 1, or for any x, you can actually factor x cubed minus 1. This is equal to x minus 1 times x squared plus x plus 1. So if you divide both sides by x minus 1, the x minus 1s on the right cancel, and this is just x squared plus x plus 1. So for x different from 1, this function is the same as this quadratic. And as x gets closer to 1, x squared also gets closer to 1. And this is approaching 1 plus 1 plus 1, or 3, as x goes to 1. So this is actually a rigorous proof of what the numerical data shows you, which is that this limit does equal 3 as x approaches 1. Now, limits often just don't exist. So let's look at the function we looked at a moment ago. F of x equals 1 over x for x different from 0. We could ask, even though this function doesn't exist when x equals 0, is there a limit as x approaches 0 for 1 over x? And the graph of this function looks like that. As x approaches 0 from the right, this function is shooting up towards infinity. As x approaches 0 from the left, the function is shooting down to minus infinity. So all we can say about this limit is does not exist. Let's look at another nice example. Suppose I take the absolute value of x divided by x. And again, this is only defined for x equal something different from 0. How is the absolute value of x defined? This is equal to x if x is greater than or equal to 0. So it's just like the line y equals x. But if x is less than 0, the absolute value of x is minus x. So the graph of the function y equals absolute value of x is this right angle curve. Well, it's not, I mean, it's a curve, but it's straight lines, just this right angle. So what is absolute value of x equal to? Well, the two cases depending on whether x is positive or x is negative. If x is positive, the absolute value of x is x. That's x over x, or 1. If x is negative, the absolute value of x is minus x, and minus x over x is minus 1.
Oh my God. What am I talking about?
So the graph of this function, it's not defined when x equals 0, but for x bigger than 0, it's 1. For x less than 0, it's minus 1. So again, the limit of f of x for this function as x goes to 0 does not exist. You could say the limit from the right as x goes to 0 through positive values is equal to plus 1. The limit as x goes to 0 through negative values is minus 1. But the limit itself, without this restriction on the right side or the left side, doesn't exist. Now, there is a formal definition of limit, which I'll state, but it's really just to show you that in mathematics, one gives formal definitions, but they have to encapsulate your intuitive understanding of what things means. So we want to understand, what does it mean to say that a function f of x, as x approaches a number c, has the limit L. So if you think about that, let's say this is C, this is L. And what we mean is we don't evaluate the function at C, but we say, suppose we take some small interval around C, say C plus delta and C minus delta. So in mathematics, we like Greek letters, and delta, this is a lowercase letter delta, just as this is a lowercase letter epsilon. And to say that the limit of a function f of x as x approaches c is equal to L means if you take any little narrow strip around L, no matter how small you want to make it. So for any epsilon greater than 0, this is the horizontal line L plus epsilon. This is the horizontal line L minus epsilon. And it says that if you're close enough to C, within delta to the right or the left of C, the graph of the function is within epsilon of L. So the graph of the function is always in there somewhere. And so as you get closer and closer to C, the function gets closer and closer to L. And there is a formal definition. It is that the limit of f of x as x approaches C is equal to L means that for every epsilon greater than 0, no matter how small you make it, just any epsilon greater than 0, there exists a delta greater than 0, such that if x is close to C, within delta of C, so the absolute value of x minus C is less than delta and greater than 0. We never let x equal to C. But if x is in this interval within delta of C, then f of x is within epsilon of L. So f of x minus L is less than epsilon. And most of calculus consists in computing one kind of limit or another. The most important limits are limits that define the derivative, which we study a lot in this course, and also the integral that we introduce at the end of this course, and you spend a lot of time investigating in Calc 2 and Math 176. This is the definition of a limit. Any questions about this? There's homework for next week or whenever the homework 2 is on limits. Let me do 1 or 2 problems just so you get to see what they're like. So some of these are computational. You just take your calculator and you work out some numbers, and some involve looking at the graph of your function. So, for example, in this section 2.2, exercise 17, you want to find the limit of the function x minus 4 as x goes to 3. And if you look at the graph of the equation, y equals x minus 4, this is the line with slope 1 and y-intercept minus 4. And as x goes to 3, you look carefully at the graph, you see that y is approaching minus 1. Right? If you look at the graph of y equals x minus 4, as you get closer and closer to 3, the graph is approaching minus 1. That's it. Well, this is not exercise 17, but this is just an example. We look at exercise 18. Here we have a parabola, y equals x squared plus 3. When x is 0, y is 3. When x is plus or minus 1, y is 4. When x is plus or minus 2, y is 7. That's what the graph of the parabola looks like. And if we want to know what is the limit of x squared plus 3 as x approaches 1, well, on the graph, you're approaching this point. Coordinates of that point, 1, 4. This limit is equal to 4. Okay. So again, on YouTube, there's a lecture covering section 2.2. And these sessions are really to answer questions and to work examples. I'm also going to have a couple of office hours tomorrow. Office hours are always completely optional. I'm just available on Zoom to answer questions and to solve problems. So I'll post a time. There'll probably be 2 times tomorrow, one in the morning and one in the afternoon, when I'm available for answering questions. But if there's nothing else right now, then I think we're going to stop. Any questions about anything that, calculus starts pretty slowly because we follow the syllabus. And lesson 1 was the pre-calc review. And lesson 2 is this introduction to the concept of a limit. And there's some homework problems that will try to reinforce what they mean. Any questions at all? Any questions about how you submit the homework to Blackboard? Okay. If not, then we will end for the morning. But I'll be available again a couple of times tomorrow. I'll send an email and post on Blackboard the times. And then we have another review class or another problem session class Wednesday morning at 11 o'clock. Okay. Bye all.